Section: Introduction. In this section, we discuss recent advancements in artificial intelligence, such as language modeling, image synthesis, and reinforcement learning, which suggest a future where AI systems seamlessly integrate into our daily decision-making processes. These systems often work independently to achieve the goals of their users, but this individual optimization can sometimes lead to conflicts, especially in tasks that involve both cooperation and competition. Social dilemmas exemplify scenarios where each agent's self-interested actions can result in outcomes that are less beneficial overall compared to if they had cooperated. A prominent real-world example of a social dilemma is the issue of climate change, where individual and national economic interests clash with the need for global cooperation to address environmental challenges. The complexity of aligning individual actions with the common good is further complicated by the rapid and opaque decision-making of machine learning systems, making it difficult for humans to oversee every choice made by these systems. Therefore, there is a critical need to develop methods that enable agents to autonomously align their interests with each other. Traditionally, deep reinforcement learning has focused on fully cooperative or fully competitive settings, overlooking the nuances of social dilemmas. Studies have shown that basic reinforcement learning algorithms tend to reach suboptimal outcomes in social dilemmas like the iterated prisoner's dilemma. To bridge this gap, opponent shaping algorithms like learning with opponent learning awareness, LOLA, have been introduced. These algorithms influence the behavior of other agents by assuming they are naive learners and adjusting their strategies accordingly. Other opponent shaping algorithms have also shown success in partially competitive tasks. A new approach called LOQA proposes a different form of opponent shaping by controlling the value function of other agents. This method offers computational advantages over previous techniques and lays the groundwork for the advantage alignment algorithms. Advantage alignment is a family of algorithms designed to shape rational opponents by aligning the advantages of different players. By focusing on maximizing expected returns and actions proportional to these returns, advantage alignment simplifies opponent shaping without the need for complex parameter updates or gradient estimations. Social dilemmas are prevalent in various human interactions, and our research specifically targets designing climate negotiation strategies that promote cooperation without centralized control. By applying advantage alignment to complex scenarios like the negotiation game, we aim to address challenges at scale and provide insights applicable to real-world interactions. Our key contributions include introducing advantage alignment and proximal advantage alignment, demonstrating how existing opponent shaping algorithms implicitly align advantages, and extending opponent shaping to continuous action environments with promising results in the negotiation game variant. Section Summary. In this section, we explore the concept of social dilemmas, which arise when individual optimization leads to suboptimal outcomes for all involved. We delve into the challenges of aligning individual interests with collective well-being, particularly in scenarios like climate change negotiations. Our focus is on developing advantage alignment algorithms that shape rational opponents in reinforcement learning, aiming to address complex real-world interactions such as the negotiation game. Section: Markov Games. In this section, we examine Markov games. We look at fully observable, general-sum, n-player Markov games represented by a tuple M equals N, S, A, P, R, gamma. Here, S is the state space, A is the joint action space for all players, P maps from every state and joint action to a probability distribution over states, R is the set of reward functions, and gamma is the discount factor. When it comes to reinforcement learning, we have two agents playing a Markov game, 1, agent, and 2, opponent, with policies pi_1 and pi squared, controlled by theta_1 and theta_2 respectively. Value-based methods like Q-learning and SARSA estimate the discounted reward using the Bellman equation. In policy optimization, both players aim to maximize their expected discounted return using a reinforce estimator. Opponent shaping, introduced in LOLA, assumes the opponent is a naive learner and shapes their behavior through an imagined naive update. LOQA assumes the opponent's policy is based on Q values. The key idea is that these Q values depend on pi caret 1, allowing the opponent policy hat pi squared to be differentiated with respect to theta underscore 1. Advantage alignment simplifies opponent shaping to its core components to derive it from first principles. The main goal is to align the advantages of both agents to steer towards mutually beneficial trajectories. This alignment is captured in the advantage alignment formula, which focuses on maximizing the probability of actions with high product between the agent's past advantages and the opponent's advantages at the current time step. This formula leads to a proximal surrogate objective similar to the PPO formulation, used in the proximal advantage alignment, proximal add-align algorithm. This assumption is crucial as it allows the agent to influence the opponent's learning dynamics by controlling action values. Section Summary. In this section, we delve into Markov games, which are fully observable, general sum, n-player games represented by a tuple. Reinforcement learning in Markov games involves two agents optimizing their policies to maximize expected discounted returns using methods like Q-learning and SARSA. Opponent shaping, introduced in Lola, manipulates the learning dynamics of opponents to incentivize desired behaviors, with the key concept being advantage alignment, where agents align their advantages with those of opponents to steer towards mutually beneficial trajectories. Section. Interpreting advantage alignment. In this section, we interpret advantage alignment. The equation provides 4 cases for controlling the gradient direction of the log probability of the policy. The sign in the equation indicates whether the probability of taking an action should increase or decrease, similar to the usual policy gradient estimator. We present 4 quadrants in a table, each corresponding to different signs the two advantages can have. We explain the meaning of each quadrant: cooperative, empathetic, vengeful, and spiteful. In the cooperative quadrant, both advantages are positive, so it is rational to increase the probability of the action as it benefits both the agent and the opponent. In the empathetic quadrant, the sign is negative because the action harms the opponent, leading the agent to decrease the probability of taking that action despite benefiting itself. The vengeful quadrant also has a negative sign, but here the action harms the agent, causing a decrease in the probability of taking it, even though it benefits the opponent. In the spiteful quadrant, where both advantages are negative, the probability of taking the action increases, despite harming both agents, which may act as a deterrent. We then connect existing opponent shaping algorithms to advantage alignment, showing how these algorithms exhibit the behaviors of cooperative, empathetic, vengeful, and spiteful. Theorems demonstrate the relationship between opponent shaping algorithms derived from Lola and advantage alignment. The opponent shaping term in Lola's update is shown to align with advantage alignment, while LOQA's opponent shaping term differs only by a scalar term. Moving on to specific game scenarios, in the iterated prisoner's dilemma, advantage alignment agents display a tit-for-tat strategy, cooperating initially and then mirroring the opponent's previous move. In the coin game, where agents collect coins, advantage alignment agents aim for a Pareto optimal strategy of collecting only coins matching their color. The agent's performance is compared to LOQA agents against various policies, showing different cooperative behaviors based on masking different quadrants. In the negotiation game, modifications are made to create a fair setting for advantage alignment agents compared to PPO agents. The game involves bargaining over items with public values, one-shot negotiations, and a reward function based on proposals. The social dilemma arises as agents are incentivized to maximize items but achieve lower returns compared to a cooperative strategy. Advantage alignment agents successfully solve this social dilemma by cooperating with themselves and remaining non-exploitable against always defect strategies. Section Summary. In this section, we interpret advantage alignment by examining the direction of the gradient of the log probability of the policy, which leads to 4 distinct cases based on the signs of the advantages for the agent and opponent. These cases are labeled as cooperative, empathetic, vengeful, and spiteful, each representing different behaviors in decision-making. By relating existing opponent-shaping algorithms to advantage alignment, we show how these algorithms embody these four behaviors and how they are interconnected through the concept of advantage multiplication. Section: Related work. In this section, we explore previous research related to the iterated prisoner's dilemma, IPD. We learned that tit for tat was identified as a strong strategy in IPD tournaments. Recently, strategies in IPD have been found to manipulate rational opponents into cooperating for their benefit. Researchers showed that when two Q-learning agents play IPD, they tend to both choose mutual defection, which is not the best outcome. It was also observed that policy gradient methods lead to the same suboptimal result. By using optimistic initialization and self-play, Q-learning agents can discover a Pavlov strategy in IPD. Opponent shaping, introduced in Lola, helps control how opponents learn in a game by assuming they are naive learners and updating their strategies accordingly. Variants of Lola have been developed to ensure stable learning dynamics, consistent updates, and independence from specific policy choices. Another method involves having an agent play against an approximation of the best response to their policy. Our work, based on LOQA, uses reinforce estimators to shape opponents by adjusting their Q values. In a broader context, some approaches model games as metagames to find socially beneficial equilibria. For instance, a continuous adaptation framework for multitask learning uses meta-learning to handle changing environments. Meta-value learning employs neural networks and Q-learning to predict the impact of policy changes in games. The negotiation game, a benchmark for studying general-sum games, requires agents to balance cooperation and competition for optimal outcomes. Future research will focus on a more complex simulation involving negotiations on climate change, aiming to provide insights into negotiation strategies in real-world scenarios to aid global policy decisions.